Hello. In a previous video we talked about immunization and we developed a model that worked under a set of very restrictive assumptions. So what we will do now is to work to lift those assumptions. Okay, so to do that we first need to introduce this new concept of convexity, right? So first, definition. The convexity is basically the second derivative of the price of a bond with respect to interest rates, okay, as you see here. So we are still in the same framework as we were when we developed the duration concept. Namely, we are thinking about parallel shifts in the curve, and these R denote the common level of the curve. So if we change this R, the whole curve changes by a given amount. So there's a parallel shift, right? So again, the convexity is the second derivative, and similar to what we did with duration, we divide by the price just for convenience, for historical reasons. Again, the important thing in all these concepts of duration and convexity, it's always this idea of derivative, okay? So why do we want to use this convexity? Well, the idea is that the price of a bond is not a linear function of interest rates. So when we expand the price in a Taylor series, we get more terms than just the first order term. So this would be the expansion of the price up to the second order, and then all the higher order terms, third order, fourth order, and so on, are over here. Okay. So if we ignore these higher order terms, we can say that the price change, or the proportional price change, is approximately equal to this expression. So up to here, this is what we have used before, which is just to use the duration concept, so the first order term. And what we are saying now is that we can do a better approximation by including the second order term, so the second derivative. And as we just defined, the second derivative divided by the price is going to be called convexity. Okay. Before we move on, just note these two remarks that you have here, which is kind of interesting, which is duration may be good or bad, in the sense that depending on the sign of interest rates, I may want to, on the sign of the interest rate change, I may want to have higher or lower durations, okay, because the sign here is important. But that's not the same thing with convexity, right? So convexity, as you can see here, multiplies the change in rates squared, so this always becomes positive, meaning that regardless of the interest rates going up or going down, I always prefer to have higher convexity, in the sense that the higher the convexity, the bigger the positive increase in price. Okay. What I said has to be qualified with this footnote that you have here, so please read through this. We can discuss this more in class. All right. How do we compute the convexity of a bond? Well, it's exactly the same idea as we did for duration. That is, we are going to define two rules, and then with these two rules, we can compute the convexity of anything. Okay, first rule. Exactly the same thing as for the duration. We start with a zero coupon bond. So in this case now, the convexity of a zero coupon bond is just the time to maturity squared. Okay, duration was the time to maturity without the square. Now we put the square for the convexity. Okay, I mean, this is not a definition. This comes from the definition, and the proof is here. You can look through this if you like. Right? Quick example. So let's consider a 20-year zero coupon bond, and let's assume that the interest rate, the discount rate, changes from 5 to 3%. Okay, and let's approximate the new price of the bond with these different terms that we have so far. Only the duration, as we have done before, and now with this new convexity. Okay, so let me open this. Okay. So again, this is the expression that we had in the handouts. The new price, this P star, is the old price plus the change in price. And the change in price, using the Taylor expansion up to the second order, is this part here. Okay. Okay, the old price before interest rates changed, so while interest rates were at 5%, is this. Okay, so now let's do the approximation. So first, just using the duration, meaning just using the expansion up to here, so only this part. Okay, so only this. If you plug in the numbers, the old price is this number here, the change in rates is minus 0.2, and then the duration, this was a zero coupon bond, so the duration is 20. Okay, so if you plug in the numbers, you get this new approximate price. If we now use both the first and the second order terms, so both duration and convexity, so if we use this full expression here, okay, then plugging in the numbers, now the convexity is the time until maturity squared, so 20 years squared, and then the change in rate here also comes squared. So, but if you plug in the numbers, you get this value here, right, for the new price. Obviously, this example is just for us to understand how to use convexity. I don't really need to be doing these approximations because I can very easily, I mean, even with less work, compute the exact new price with the new interest rate. Okay, this is just to understand the convexity concept. So if I actually compute the exact price, the P star, with the new 3% rate, this is how much I get, right? So basically what's going on is, looking at this figure here, if I plot the new price as a function of the new interest rate, the blue line is the correct number, the exact price. So this was the price at 5%, the 0.36 that we have up there. And this is the new price after the change in rate, exact, so this number here. If I was using just the duration, just this part here, this would be a linear approximation, so I would get this approximation here, this black dot here, okay? Which, as we already know, if the interest rate change is large, the approximation may not be so good, okay? I may have a large error. But if I use both duration and convexity, I am using more terms in the Taylor expansion, the Taylor series, and therefore I get closer to the truth. So the red line here shows the approximation that I get with both duration and convexity, which is, as I said, much closer to the exact price. As you can see, it's the difference between this number here and this number here, which is quite close. So it's not the exact number, but it's a reasonably good approximation. Okay. All right. So that was rule number one, the convexity of a zero coupon bond. It's just the time to maturity squared. Okay. Second rule, the convexity of a portfolio. And this one is exactly like the rule we had for duration. The convexity of a portfolio is just the weighted average of the individual convexities. Okay, and the weights are, again, as before, the natural weights, meaning the value of each security relative to the total value of the portfolio. All right. So again, we have the two rules, and with these two rules, we can compute the duration of anything. So not the duration. Now it's the convexity. Okay. So first application, convexity of a fixed coupon bond. Again, a fixed coupon bond is just a portfolio of zero coupon bonds. So I apply that formula for the portfolio convexity and then replace the convexity of each of these zero coupon bonds by the time to maturity squared. Okay? Exactly like we did for duration. Second example, convexity of a floating rate bond. Exactly like before, we decompose the floating rate bond using the pricing arguments into a series, a portfolio of zero coupon bonds, and again apply the formula for the convexity of a portfolio and then the convexity for each of those zero coupon bonds. So this looks exactly like the formula we had for the duration of a floating rate bond. The only difference now is that the time to maturity of each of these zero coupon bonds is squared, whereas in the duration was just the time itself without the square. Okay. Quick example. So let's consider the following portfolio. We have two assets. The first one is a 6-month deposit of $2 million. Okay. And the second is a 2-year strip. Recall that the strip is just like a zero coupon bond with a face value of $3 million. Okay, so that's the amount of money I'm going to get at the end, 2 years from now. And I know that it is offering a yield to maturity of 4% with annual compounding. Okay, so let's compute the convexity of this portfolio. Okay, let me open the figure. Here it is. All right. So the first asset, again, it's a 6-month deposit. It has the value of the money that I actually deposit now, $2 million. Okay, and the convexity, this is a 0 coupon bond, is just the time to maturity squared, so 0.5 years squared. Then we also have the 2-year 0 coupon bond, or the 2-year strip, with a face value of $3 million, which has a current value of the present value of the 3 million. So 3 million discounted at the rate was 4% with annual compounding. So that's it. Okay, that would be the value of the bond today times 0. And the convexity, this is a 0 coupon bond, so it's just 2 years squared. Okay. Then the convexity of the portfolio of these two assets is, again, the weighted average of the convexities. So the first asset, the deposit, has a value of 2 over the total value of the portfolio times the convexity of the first one. The second asset has a value like this, that we just computed here, over the total value of the portfolio. So this is the weight in the second asset times the convexity of the second asset. So the total convexity of this portfolio is this number here. Okay, and I'll stop here.